Hello and welcome back, everyone. So we're moving on to section 0.4, the fundamental theorems of multivariable calculus. I should really probably call this an introduction. Let's recall what we were doing in the last lecture. We learned about domains as sets, and these were open, connected subsets of Rn, some higher dimensional space. We also learned about multidimensional functions. Which had the ability to have multiple inputs and multiple outputs. And in fact, they're kind of the most well-behaved when the function's domain, in the sense of functions, is a domain in the sense of sets. That's why we kind of use the same language of domains between the two of them. And more or less, we're trying to set ourselves up to think about calculus in higher dimensions as an ability to integrate or add lots of tiny pieces of functions over a domain and what that might mean. So let's think about it all the way back. I know we just keep going back to one-dimensional fundamental theorems, but let's go back to the fundamental theorem in one dimension. When we compute the definite integral, some x minimum to x maximum value of a function, let's just draw an arbitrary function here. And we're computing the definite integral from x min to x max, right? We're computing kind of the signed area that's going on there. However, we should really think about this interval along the x-axis as a domain. So let's call that interval omega. The interval x min comma x max. And then when we think about integrating, performing a definite integral, what we're doing is we're taking the value of f of x at this point, and we're adding it to the value of f of x at the next point, and the value of f of x at the next point, the value at the next point, value at the next point. We add all of these together, right? It's in some sense, the integral is an infinite sum. That's why we use kind of this S shape for sum, because the integral is a sum. So we're summing values of the function f all along the domain omega. So let's go ahead and rewrite the integral from x min to x max now really is s. It's still an integral sign, but think about it as a sum of these values of f of x. And in fact, these values are going to be multiplied by dx. Whatever that means. We'll accomplish the definition of dx later. And then we can say all along, all over the domain omega. So how have I written it here? It's the signed quote-unquote total accumulation of f, whatever that means, over its domain. That's what we're going to think in higher dimensions as well. It's going to give us the ability to develop higher dimensional integrals. Now, we're not going to really get there today, but it's just us trying to think that, yeah, our one-dimensional function kind of has the ability to generalize to higher dimensions if we want. As many dimensions as we would want to choose, because, you know, some notion of total accumulation of f, kind of arbitrary how many dimensions you're in to just accumulate something over a domain, also arbitrary dimension. We also saw in our fundamental theorem of calculus statement that we had the following two statements. It's the first and second fundamental theorem. If I take the derivative of the integral, where the upper bound of the integral is the same variable that's in the derivative, they're going to cancel each other and you just get the original function. And similarly, if I take an integral where the upper bound is a variable of a derivative of a function, that variable is just going to become the evaluation on the inside of the function. And in fact, this happens on the lower bound as well. So in terms of domains, we can really replace this interval x min comma x with the domain omega as a function of x, right? Domain as a function of x. And what that allows us to do is now rewrite, at the very least it allows us to rewrite the left-hand side of our fundamental theorem of calculus in terms of domains rather than bounds on the integral. And in fact, the right-hand side, specifically of the second fundamental theorem of calculus, gets very interesting. We can think about an evaluation of f on the boundary of the domain. Because what is if I define omega of x to just be x min comma x, an interval, then its boundary is just the endpoints of the interval. And so that'll just be the points, x min and x. So now if we just take our function and we evaluate on the boundary, there's an orientation there that we're kind of pushing under the rug for now, but there's an orientation to the boundary that accounts for this minus sign, right? X min is a smaller number than x. But we do just evaluate the function on the boundary, and that's kind of something pretty special. So a multidimensional equivalent, if I just directly decided to replace omega with a multidimensional domain, f with a multidimensional function, maybe even x or c with multidimensional variables, I'm just going to directly replace all of them. And we recover, the following. So I've just kind of made everything in bold to try to refer to the fact that this x is multidimensional, this omega is multidimensional, c is multidimensional, and f is multidimensional. And so that's kind of what we would love to achieve. Unfortunately, there's not really a good way to achieve statements exactly like this. There's ways to achieve statements kind of like the second one. We kind of recover this, but it will take us most of the semester. And in fact, we don't quite write it like this either. We kind of allow this dc and that dc to cancel, and we just write d of f of c. And then on the right-hand side, we don't call this like an evaluation on the boundary. We're going to end up calling the right-hand side actually an integral over the boundary. So we'll have to figure out exactly what that means in a multidimensional setting later. But let's try to understand what something like d dc or d dx, where x has multiple dimensions, could even mean. And the best way to think about that is this this notion that mathematicians have come up with of the partial derivative. I mean, we're eventually going to even get better derivatives and partial derivatives. For now, let's just talk about the notion of the partial derivative. Now, you've already seen this thing called partial and boundary. Turns out partial derivatives are somewhat related, but it's an obscure reason that I won't get into. So we have something called a partial derivative that I want to introduce, and I want to show that we really kind of experienced them already. What do I mean by that? Well, before I even define the partial derivative, even naively, I'm going to say that we've had a prior experience with this thing that I'm calling a partial derivative. So let's just take the one-dimensional function, ax squared plus bx plus c, kind of your standard quadratic. And if I asked you to take a derivative of this function, I think you would do it just fine. How would we take a derivative of this? We'd use the power rule. We would get, well, the 2 would come out front. We get 2ax. This x would just become 1 plus b, and the c would become 0. So you'd say that the derivative is 2ax plus b. Aren't a, b, c variables? I mean, a lot of you would say no, they're constants. And then I would turn around and say, are they? We could allow a, b, and c to be variables, and yet you were still able to take a derivative. So if I decide to rewrite my function f as a multidimensional function with 4 inputs, these inputs being a, b, c, and x, you could still take a derivative the same way we just discussed, where you get 2ax plus b. It just turns out that this notion of a derivative, when a, b, c are variables, is the partial derivative. Okay, so you've seen these partial derivatives before, except we haven't really called them partial derivatives. We've kind of assigned everything else to be a constant and then just taken an ordinary derivative. And so you've seen maybe some other cases, if you want to take the arbitrary power rule, right? How would I take d dx of x to the n? You just pull the n down, you say x to the n minus 1, if n is constant. But this is a partial derivative if n is a variable. And similarly, maybe you want to take the derivative of e to the alpha x. You can take that derivative just fine with chain rule, you get alpha e to the alpha x. It's just a partial derivative in the direction of x. That's what the dx in the denominator is standing for. We are going to come up with different notation for these partial derivatives. It won't be d dx anymore because that's reserved for the ordinary derivative. Anyway, you've definitely performed partial derivatives before, and so now I'm going to define them. I do want to caveat that I am defining them naively. We will eventually define them rigorously later. Naively, what is a partial derivative? A partial derivative with respect to a specific variable, and so in this case I'm going to call that variable x sub I, so the ith direction or the ith input to my function. We're going to denote using those partial symbols. By the way, if you want to get used to writing these partial symbols out, I think about writing like a cursive 2 or whatever you would do, and then just ending it early. So, don't just stop your 2 before you cross through the second line, and that's how I end up with a partial symbol. So the partial derivative in the direction of xi, the way it works is we're just going to take, well, here's a multidimensional function. It's got all of these inputs. And what I'm actually going to do is I'm just going to isolate the xi input, right? I want the same input there. And this is the only input I'm going to consider. Only non-constant input. And once I view it as the only non-constant input, I'm just going to take the ordinary derivative like I would in calculus 1 of the function with only that variable as an input. And so let's get used to that. So even though this function has x, y, and z all as inputs, and of course x, y, and z all show up as outputs, if I want to take the partial derivative in x, what I'm going to do is I'm going to grab x, and I'm going to look right here and say this x is the only variable that actually exists. That y and that z are both constants. And once I realize that I can treat y and z as constants, it's pretty easy to take a derivative. I'm just going to use the power rule in x and then get 2x y cubed z to the 4th. Similarly, if I want to take a partial derivative in y, I'm just going to treat this x and this z as constants. And then I can go ahead and take my derivative of the variable y. That's going to give me 3y squared. And then the constants stay along for the ride, right? Similarly, if I want to take partial derivative with respect to z, I'm going to find z and keep both x and y as constants. Do a derivative on z, it's going to be 4z cubed. So that's how partial derivatives are kind of naively defined, but that is how we end up computing them as mathematicians. And similarly, I got another example here of another multidimensional function. Now what's special here is that g has 2 outputs. How are we going to do partial derivatives on multiple outputs? Well, you just take the partial derivative and you pass it to each output individually. So it just turns into partial derivatives of one-dimensional functions piece by piece. And so what does that look like here in the case of doing partial alpha? Well, I'm going to treat the t and the s as constants, meaning that I'm looking at sine alpha t and cosine alpha s, really just as sine of alpha with maybe some constant t and cosine alpha with maybe some constant s. So those constants are going to come through with a chain rule, but I don't have to take an extra derivative in terms of the sines and the cosines here. So if I took a derivative of sine of alpha t just in the variable alpha, the derivative of the outside is going to give me cosine, and then the derivative of the inside in the variable alpha is going to make alpha reduce down to 1, so I'm multiplying by t. That's the chain rule there. Similarly, derivative of cosine is negative sine, and then a derivative of the inside in the variable alpha will just give me an s. You could consequently do partial derivatives in t or s of that function as well. It just depends on which variable are you treating as a variable, and then you're going to let all the other variables be treated as constants. It turns out you've also had prior experiences with multidimensional integration. The same way you had experiences with differentiation or partial derivatives, you've probably done something quite similar with higher dimensional functions, but integrating. So going back to our quadratic function, ax squared plus bx plus c, if I asked you to integrate this, you would find the antiderivative just fine using the power rule. You'd say, oh, it's a, a is a constant, so then you just integrate x squared using the power rule, you get x cubed over 3, b is a constant, you integrate x with the power rule, you get x squared over 2, c is a constant, you integrate the constant 1 with the power rule, and you get x. And so you can find an antiderivative just fine in the direction, right? That's this dx here in the direction of x just by looking at each x and isolating them and computing their antiderivatives individually. And so what I've done here is, of course, I've used our newer notation. We're trying to abandon the indefinite integral as a notation. So this newer notation, now we're going to use from the integral from 0 to x, and the variable I put here is c, of course. But it's the same thing we just saw, ax cubed over 3 plus bx squared over 2 plus cx. So you've all done that before, and yet you could once again treat this function as a 4-dimensional input function where a, b, and c are technically variables. How would you integrate them? Well, you just integrate the same way you did before. Like, as long as we specify the variable that we want to integrate against, in this case c, or in my earlier case x, then you treat everything else as a constant. So you can do kind of this general power rule, x to the n or c to the n, and you just say you keep n here as a constant, so then it becomes n plus 1 divided by n plus 1. And so you get the general power rule for integrals, or maybe e to the alpha x. If you're integrating again in the c variable, you get the general kind of exponential rule for integrals with the u substitution taken into account where you're dividing by alpha there. And so you've done all sorts of this like integration even with multidimensional functions before. It just didn't feel like it. It felt like these other terms were constants. And that's all you need to know to do it in a naive way. And a naive way gets you very far. I want to make it quite clear that a lot of people, including professional mathematicians, perform partial derivatives and integrals in multidimensional settings in this naive manner. We do sometimes have to be formal, but we don't always have to be formal and rigorous about it. So let's define the multidimensional integral somewhat naively, and it's the same as we did with the multidimensional derivative. We're just going to say, hey, I'm going to look over here. I'm going to look and see what input, is this referring to xi sub I? So xi sub I is referring to the ith input, and so I'm looking to the ith entry. And of course, if we're in 2 dimensions, that could be the first or the second entry, but it's just gonna, it's gonna be told to us which entry we want to integrate with respect to, and then we're just gonna treat it as a normal one-dimensional Calc 1 integral, where that's the only variable. Everything else can be considered as a constant. And so let's do a couple examples of these. Let's say maybe I want to integrate x squared y cubed z to the 4th, where I specifically notate the first entry with xi, and I'm going to integrate from 0 to x. All that means is I'm evaluating x at xi, and then y and z are remaining, and so there you go. We've got xi squared y cubed z to the 4th, and now I'm integrating this with respect to xi alone, which means that the xi squared is really the only term that I need to find an antiderivative of. Antiderivative of that is xi cubed over 3. And I'm just going to evaluate those at 0 and x and get exactly what you'd expect, x cubed over 3, y cubed z to the 4th. And do the exact same thing in the variable y. Here, that's the Greek letter upsilon, even though it looks kind of like a v. The Greek letter upsilon is the closest thing you can get to kind of a Greek y. They don't have like a y sound in the Greek alphabet. So this is the Greek letter upsilon, and you just replace the y here with an upsilon. And then once you replace y with upsilon, you integrate specifically the one term that you replace with upsilon. So that's going to give you upsilon to the 4th over 4, and then place that to bounds 0 and y. You're just going to get x squared y to the 4th over 4 is e to the 4th. So, I mean, looking at this, if I said integrate that in the x variable, you would just say, oh, that's x cubed over 3, y cubed z to the 4th. If I said integrate that in the y variable, you'd say, well, that's x squared y to the 4th over 4 is e to the 4th. So don't overthink all of these, partial differentiations or multidimensional integrations. They are really quite straightforward. You're just kind of treating some other terms as constant. Now it gets worse than that. So don't think that you've got all of multivariable calculus solved, but this also does get you quite far. So we've got another example in this function g, which, as before, has 2 outputs. And that all that means is that you just treat each output individually when you're integrating it. So you just pass the integral to both outputs. But everything basically looks the same the way you would expect. Now what I want to say is that this does allow us to construct a naive fundamental theorem of multivariable calculus. There's nothing really preventing us from accomplishing this statement of the fundamental theorem of multivariable calculus. And the way this statement is written makes a lot of sense because it kind of reduces to one-dimensional fundamental theorems. But let's just talk our way through it and see that it's nice that you can actually come up with it. What's going on here? It looks ugly because I've thrown a bunch of x's in here and it's a repeated integration. But what are we actually saying here? We're basically saying, hey, if I integrate, let's work my integral from the inside out. If I integrate in xn first and then do these dots, right? These dots mean something. You're just repeating integration. And then eventually in x2, and then finally, let's say finally in x1. So if we integrate in every possible dimension, right? Integrate in each dimension. And then we turn around and we take a derivative, right? We take a derivative in the nth direction. We take a derivative in the second direction. We take a derivative in the first direction. Then they all cancel. So if we integrate in each dimension, then differentiate in each dimension, they all cancel. And we get what we started with, right? We get this f of all of the entries, which is exactly the far interior of all these integrals. So everything works out exactly the way you would expect it to. It's all hunky-dory. Why do we have the rest of this semester of trying to define integrals in higher dimensions? Well, I'm just going to point out one reason. The first reason is that, look at this, the domain of this function. We have an interval cross an interval cross dot dot dot. I'm trying to refer to more intervals cross an interval. So those are just intervals on top of each other. Well, I mean, they're all pointing in different directions. If we think about going back to kind of the previous topic we had, if we think about even the standard sphere in 3 dimensions, right? The sphere looks like this. So that sphere in 3 dimensions is a domain. We encountered it as a domain, so I'm going to fill it in. It's a perfectly valid domain. We could integrate over. And yet, it is not equal to an interval in each dimension. Right, there's no collection of a single x interval and then a single y interval and then a single z interval that's equal to this sphere. I mean, technically, if you perform this special x that we have between all of these, the way it works in higher dimensional space is that you're going to drag the intervals against one another, and what you end up with here is a cube, right? If I drag all those intervals against each other, you get kind of the square in the xy direction, and if you drag it against the z direction, you end up getting a cube. So you get this kind of 1 by 1 by 1 cube when all these drag against each other, and the cube and the sphere are not the same thing. And so this works for rectangular prisms, because we can, kind of stretch and skew the cube in either direction we want. So it works with rectangular prisms, but no other domains. So we're kind of stuck because we would love to do this with domains that are not rectangular prisms, and this is only giving us rectangular prisms. So something more needs to happen. I'm going to get back to that example soon, but something more needs to happen, and this remark starts talking about some other things that go wrong with our statement of the multidimensional fundamental theorem of calculus. So if we decide to look at the statement of the earlier fundamental theorem was the equivalent of the first fundamental theorem of calculus, this is kind of the second fundamental theorem of calculus. And so we're taking the repeated integral of repeated derivatives of a function. Do they all cancel? They do not all cancel. What you get instead is you get this really strange sum. You get a sum over all combinations of what I'm calling ki in the set 0, 1, with I ranging over 1 to n, and we get -1 to the power of the sum of all of these ki's, and then you're evaluating the function either at a variable or at the lower bound for each of the directions, and you're just performing this huge sum of all of these terms. In many cases, this is not going to be equal to just f evaluated at x1, x2, x3, ... xn. Right? Even that plus a constant. It's not going to be equal to that plus a constant. And so kind of the second fundamental theorem of calculus already breaks down. We just saw that even this first fundamental theorem only works for rectangular domains. And then we also have this notion that partial derivatives and integrals are computed with respect to a single variable input, right? In the sense that, like, if I write this function, sine of x squared plus y, and then I kind of display it as a surface embedded in 3 dimensions, the partial derivative in the x direction, so partial x, describes specifically that x slope, right? It's like a slope along the surface as I walk in the x direction. And so, my x direction here being the direction to the right. And similarly, my partial derivative in the y direction, partial y, is kind of the slope along the surface as I move in the y direction, right? So this y input, that's the slope that pushes me in the y direction if I'm walking along the surface there. But what about all the other directions that exist? There's a y equals x direction slope that I've drawn in the middle there. There's also a y equals negative x direction slope that I've drawn in the middle there. So all of these other slopes exist that aren't specifically slopes in the x direction or the y direction, and these partial derivatives can only consider slopes specifically in those 2 directions. And this kind of harkens back to the rectangular prism, right? If I'm integrating over these domains, they're all like flat and in specific directions parallel to the axes, right? So we can't really do any calculus in directions that aren't parallel to the axes that we've drawn. So that's like a kind of not a good thing to do. We would like to have fundamental theorems of calculus that work for like this non-x or y slope, right? The y equals x direction slope. That's a slope that's neither in the x direction nor in the y direction. It's something in between. And we should be able to come up with a fundamental theorem of calculus that accomplishes what it should in that, with derivatives taken in that specific direction. And so there's lots of kind of like pretty substantial problems with this naive fundamental theorem of calculus. It's a good theorem. It does exactly what it says, but there's so much more that we could ask out of higher dimensional spaces. Let's apply it once, and then let's look at, the best thing we do have as mathematicians in multi-dimensions. So we're just going to go ahead and apply the naive fundamental theorem here, just so we get a little bit of practice with it. I'm going to go ahead and take this function. I'm going to integrate it in both directions. So integrate in x and in y, and then I'm going to go ahead and take the derivatives secondly afterwards. So if I integrate in x and y, well, how does that work? I'm going to integrate inside and then outside second. So if I integrate inside first, that's going to be the integral from 0 to y of epsilon over 1 plus c squared d epsilon. And so how am I going to integrate in the epsilon direction? Well, the nice thing about when I'm integrating in the epsilon direction means this denominator is a constant, And so I'm really only performing the integral here. I'm taking the antiderivative of epsilon with respect to itself. Well, the antiderivative of epsilon with respect to itself is just epsilon squared over 2. And I'm going to evaluate on the bounds 0 and y. And that's going to give me y squared over 2, just like you'd expect. So that's the antiderivative in the y direction. And then we'll perform the antiderivative, the remaining antiderivative, right, in the x direction, or the xi direction. So I've substituted xi into there. And that antiderivative is just going to be this one here. If you don't remember your derivative of inverse tangent, it does happen to be 1 over 1 plus x squared. So that's going to be the antiderivative here. We end up with inverse tangent of xi, evaluate at the bounds, and we're just going to get inverse tangent of x times y squared over 2. That makes a lot of sense, right? If I just went back to the original function and I said integrate this function once in the y variable, once in the x variable, you would say the integral in y is y squared over 2. The integral in x is really, the integral of 1 over 1 plus x squared, which is arctangent of x. And so you'd say that's the integral once in the y variable, once in the x variable. So now we're going to take the derivative, the partial derivative in the y variable here. And of course, the way we define partial derivatives, it only sees the y variable. So we take a derivative in the y variable, we get y. And then we're going to take a partial derivative in the x variable. It only sees the function in the x variable. So we're taking a derivative, typo, in the x variable of inverse tangent. We're going to get 1 over 1 plus x squared. And we end up exactly where we started. Right, and so that's just like evidence that this naive fundamental theorem of calculus does actually work for us. It is a perfectly valid theorem. It's just maybe not as useful as it initially seems. Anyway, that will send me to kind of the final statement we're going to make for today, which is the statement, even though we're not going to try to understand it yet, the statement of the generalized Stokes theorem, which is the best object we have for the fundamental theorem of multivariable calculus. What this theorem says is that very specific mathematical objects, which we will encounter eventually, which are functions from a multidimensional space to this new space that we're just calling omega k r to the k. It's the space of differential k forms, something we haven't experienced yet. But we're going to take f as a differential k form. And then we're also going to have, these are two different omegas. I know it's very annoying. Mathematicians still like to doubly use things, and we have to use context clues. We have a new omega, which is now a smooth orientable domain. We're not going to worry about these words smooth orientable at all in the course. We did learn about domains at least. We have a differential k form and a smooth orientable domain, and we decide to integrate the differential, one more derivative of the differential k form actually. We decide to integrate a derivative of this thing. Then the integral of the derivative will be equal to the integral, and it's a closed integral here. That's what the circle means. A closed integral over the boundary of the domain of the k form without a derivative. So this derivative disappears when we integrate, which is a statement of the fundamental theorem of calculus, right? A derivative disappears when we integrate. It's exactly how we define fundamental theorem of calculus. We're just going to have a lot of fun, majority of the rest of this course, trying to slightly understand what's going on in this statement. To perfectly understand it with these words smooth and orientable, unfortunately, you do need a graduate course, but we're going to have a lot of fun trying to understand it as best we can. Anyway, that concludes chapter 0, because then we're going to get into more of the nitty-gritty details so that we can understand everything a lot better. And we're going to learn a lot along the way. It's going to be a great course. See you in the next one where we're introducing linear algebra. Bye.